Sì, l'ho provato prima, poi...
L'unico consiglio che ti do è mettiti questa task. Questo sotto. Adesso quando dovresti parlare.
Prova. Si sente un forte respiro. Eccolo.
Abbassalo.
Qua ci sono i trucchi del mestiere.
Vai,
Però,
respira.
però
Vai.
sono da un dottore. Top. E mi sentite? Vabbè che la sala comunque è piccola. Ma lo catturiamo anche da qua, per online. Ma forse fanno loro l'intro prima.
Sì,
Quindi
però
forse,
sotto c'è ancora mezz'ora.
quindi forse serve a loro prima.
No, no, ce l'ha.
Ah, ok.
Ah, la musica dici. Sto fermato. Sì, appena metto slide così non è così.
Ah, già, sì.
Solito sono i principini. Qua dovrebbe esporre una robina in particolare.
Faccio anch'io. Vengo a vedere com'è lo stream.
Un po' giallo, ma
Un po' giallo.
ah, guarda,
Ah, devi togliere il profilo Night Shift dal computer.
dici che sono io?
Mio.
Sì.
Ah, lui?
Sai che io l'ho spento. Flux is off. Ah,
Anche l'altra volta era successo così.
Ma non è l'adapter che fa quel colore
È
strano?
la Night Shift del Mac.
Vabbè, sti cazzi. Un po' di giallino.
guarda, io l'ho spento.
A parte che lo vedi molto poco.
credo.
Prova un po'. No, sicuramente sono anni 70.
Schedule off. Oppure... ah,
Che piace.
col carta? Beh. Seppia. Seppia. Cosa devo fare? Il Mac dice che ho il night shift spent. Flux è spent. Faccio un restart del computer. Tipo... infatti adesso ho provato ad attivarlo. Quindi adesso lo spengo.
Mi sa che conviene che scendiamo. Mi sa che conviene che scendiamo perché c'è già la gente che spera. Ok, adesso dovrebbe essere a posto.
Com'è ora?
Adesso sì, adesso va.
C'è già c'è la gente? Sì. Ah, ok.
No, perché non lo spegnevo da mesi. Non volevo, sai, rompere il record oggi.
Forse è il mio che
Posso fare anche questo. Spegniamo Slack, tutto. E se faccio così. Sì. No.
La playlist retro wave forever. Ah, ciao, hai trovato il...
no, lo giuro aiutare per
Ah.
far portare il cartello.
sì.
No, che non ci dà infatti adesso vogliamo ancora un po'.
Mhm. Come? Sì, 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 vabbè.
Abbiamo il quarto d'ora a casino.
Che conosciamo, va bene. Va bene, va bene. Non so. Ma che ti volevo dire? Per la lingua? Vuoi che lo teniamo comunque in inglese?
A parte come
Sono io, sono io, sono io. E questo per svegliare tutti.
Si può avvicinare, può stare a distanza di sicurezza.
dicevo, sì, già ce la sono un po' rovinati.
Forse anche per chi è online.
Sì,
Aiuta
infatti l'ho
che
anche
ci sia in
pubblicato in
inglese.
qualche posto dove non parlano così.
Ah, ok.
So hi everyone, welcome, and thanks for being here. It's the first time in a long while since we have hosted this meeting. I'll start with a couple of words about what Papers We Love here is, and first of all, thank you for coming. So I don't know how you heard about this. Please do spread the word. This is the first Italian chapter of Papers We Love, and as far as I know, at least. And the idea is to share beautiful paper with beautiful people like you are, and of course with a wider audience. We want to create a network of people who enjoy studying computer science, reading papers, and learning about computer science, even though they may not be computer scientists. Connecting academics, startups, and research and development groups in Milano. So this is, well, I'll leave the word to our speaker in a couple of seconds. I have a few links for you. So if you are not following us on Twitter yet, this is our handle. There's a github.com link where you will find the papers that we discuss. This is the link through which you have bought the tickets, so probably you won't need it. And we also have a Discord, so if you want to chat with us and our speakers, if they join, you will find us there. So if you're interested, please do log in. Oh, and if this meeting was, you like this meeting and you would like to present something in the future, this is a link to our call for presentation. So it's a small form that you can fill with your details and the paper or the title of the abstract that you would like to present. I think that's it for this small presentation. Of course, we want to give a big round of applause for eDreams for hosting us tonight. So thank you. I think we also have some links to share here. Okay, so this is for the Wi-Fi. This is a career for the careers site where you can. How many people you are hiring here? 500, I think. So about 500 people. So you may probably find something that interests you. And these are the future events. Next week there's a Java user group, but there are more that are being scheduled. So do keep in touch. Do you want to add something? Sure.
Hello, everyone. A brief introduction over eDreams. Well, how many of you know eDreams? Okay, some of you. eDreams is a tech company that operates on the travel industry. So we are spread in Europe between Spain, Italy, Portugal. And in Italy, we are here in Milan. We just opened this brand new tech lab. As Edo was saying, we are hiring. So if you are up for a challenge or you are interested, just after the talk, ask me or the other guys with the line art, and we can give you more information. Okay? Thank you. Okay, so we can start with the talk. There is Giuseppe Attanasio that will talk about ChatGPT. Yeah, sort of. So nothing. Applause to Giuseppe.
Can you hear me? Okay, cool. Okay. Yeah, nice to meet you. Nice to meet you all. Thank you for the organizer for inviting me. Um, I'm Giuseppe Attanasio, and today we're going to be talking about recurrent neural networks. That's what we call, very generically speaking, recurrent models, and then some breakthrough that we had in the AI field, which is the attention mechanism. So it's not going to be a talk about a very specific paper, but rather a list of papers that, have been seminal papers in the field, especially for the NLP field. So my orientation is on NLP stuff, but so it's a collection of papers. So before we actually get started, that's a very short summary of my activities. I'm a postdoctoral researcher in Bocconi. The research group is MilaNLP, and I mainly work on transformer models. I have been working on hate speech detection, so filtering contents most of the times on social media, and specifically what we can do in sense of bias and social biases that these models learn from data. But then we have been doing some works on interpretability of those models, because the overall discussion on black boxes and understanding what's going on those models, and then vision and language, bridging vision and language. So since we are discussing about NLP stuff, you probably have heard about ChatGPT. I don't think we are far from a technology that will be published soon that will answer with images that are coherent with your textual query. So it's something that bridges the two worlds. It's something that it has been around in the field from a while now. So speaking of which, let's start with a quick, survey. How many, just by raising your hands, how many of you have heard or used ChatGPT? Okay, cool. It is, somewhat expected. What about BERT, bidirectional encoder representations from transformers? Okay. What about the transformer, the neural network? Okay, still some hands. I see still some hands. What about the attention mechanism? Okay, there's some hardcore guys here. What about recurrent neural networks? A very peculiar, you know, artificial neural network. Cool. So even from this very short and non-representative survey, we have seen that there is this very different public perception, public outreach that those models, those technologies have been, given the field. So we are in a area where, technologies are part of our everyday activities, but there is some sequentiality on how those technologies are being developed. So people were doing something with recurrent neural networks. You probably have heard of LSTMs. And then on top of those, because we needed to fix something, we built the attention we, very inclusive, we, it's not me, but we built the attention mechanism. On top of the attention mechanism, Google's researcher built the transformer, and then from there everybody went crazy because the transformer is, we can say that it's safe to assume that 99% of technologies today are based on, like, AI-based solutions, and technology are based on some sort of a transformer, or let's say an attention mechanism. There's some attention mechanism, at the core of the way we process input data. And of course, a lot of transformers, a lot of data, some, smart tricks, and you have ChatGPT. So, as I said, we're going to be talking about recurrent neural networks, recurrent models. So this is mostly the outline, and then there's a second part of the talk where we discuss the attention mechanism, why we needed the attention mechanism. We're not going to discuss about the transformer or the technologies that went, like, from the transformer on, but I think it's interesting to see where, what's the seed of everything, where we started, and where, like, how the things evolved from there. So I'd rather keep the talk, like, interactive, so maybe if you have any question anytime, just feel free to interrupt me, because or if it's boring, you just do something else. Okay, before we actually get started, two short disclaimers. I'm gonna be talking about the intuitions, so I just want to deliver the message. So if there's any machine learning expert in the room, NLP expert in the room, bear with me, just trying to deliver the message. And second, we are discussing about those technologies in a historical walkthrough. Like, I want again to discuss about how things evolved over the years. And if we were to look at the time span where those technologies evolved, we are somewhat in between 2010 2016, where if you plot the trending topics, the recurrent models, where this is some sort of a interest of the field in recurrent neural networks, and then by the end of this 2016, people just went crazy with attention. Like, the paper attention is all you need. I think it's one of those papers that like a breaking through solution, like a very seminal paper for what we are doing today, not only on NLP, but also on vision and many other applications for AI. So let me get everybody on the same page about neural networks, because before coming here I didn't know what the audience would have been likely to be. So a neural network, from a very high perspective, is some sort of mapping function, transformation function. I have an input X and I have an output Y, and I go from X to Y through the neural network. That's the transformation. And so in a typical supervised stuff, we have this sort of transformation. The trick is that I can tune and change the parameters of the neural network to solve a specific task. How do I encode the task? It's because I have some sort of loss definition. So I have an objective. I want to, most of the times, minimize my loss. And then, so I can, given the output, I have what's the expected output, so I can compute the loss. And then there is this, the linear representation by backpropagating errors paper is just the one that introduced the backpropagation algorithm, which is, I would say, one of the most influential and, elegant algorithms for AI, at least, learning neural networks. So we can compute the gradients, and we can use the gradients to tune the parameters of the neural network to solve the task. So what ChatGPT is using, then today I think I'm gonna make many references to ChatGPT. What ChatGPT has been trained for, it's just like something that resembles. You can, if you disassemble the pieces, it's something that resembles this slide. So again, I don't know about your background, so bear with me if it's too simplistic, but it truly is. Let's go now about recurrent neural networks, if there are no questions so far. Okay, so why are we talking about recurrent neural networks today? Because RNNs were specifically designed to solve tasks where the data is oriented over time. And there are many examples of data that comes in a time fashion. Stock prices, the measurements of a sensor, any kind of sensor, or I don't know, even text. If you imagine the text, the dimension, the time dimension is the unrolling of the sequence, every time step is just a word or a token. Like we generally talk about tokens, because it can be a word, it can be a character. So the RNNs were specifically designed for taking into account, for factoring time in the neural network. And if you look at the slide, it's very, it resembles what we have seen in the slide before. There is an input X, there is some what we call indent state, which is a dense representation. It's just a vector of floating point numbers, and then which we call X, H. And then we have some transformation that goes from H to Y. Now, how do we encode time? How do we factor in time? It's just the most easy way of doing it is just adding this self loop. So what we are saying here is that the hidden representation H is not only dependent from the input X that I have at this specific time period, but also it depends on the previous version of the hidden state, as if we were tracking as if we had some sort of memory in the neural network. So it just like this is something that you encode very, very in a very simple manner by having 3 matrices, which are, to go from X to H, you just compute, the product between X and the matrix, the first one, and then you can also the H, the new H, is dependent also from its previous state, so its previous version. So we are kind of keeping track of time. We are keeping track of time by keeping track of memory in the neural network, and then we have a final transformation which goes from H to Y. So if the as we said, the input can be anything, can be your ECG measurements, for example, and you have time from left to right, you can just unroll the network, which is just a visualization because the hidden cell is just one. We can unroll the network and see how the dependents are evolve over time. So, for example, to compute the output Y2, we need the input X2, but we also need we need, of course, the hidden state H2. Oh, we live in the future. Okay. I need H2, but H2 is dependent on H1, which is dependent on X1, which is dependent on H0, and so on. So we're kind of, including the past in the representation that H uses here and at every time step. And of course, when we have for each time step, we are computing some loss at every time step. And when we say that we are doing, you hear backpropagation through time a lot. When we say we are doing backpropagation here, it's through time, because when we are backpropagating from, let's say, y3, we are updating in a way all the previous steps that every previous step will give a contribution in the updates, in the current update of the parameters. So this is a very high level overview. You can find this, similar representation of recurrent neural networks in textbooks, just pretty much like this. But then people realized you can, go crazy again, so you can stack one hidden state on top of another, so your first hidden state doesn't produce directly the output, just produces another hidden state, and then you have the output. You just need to another matrix at the end of the day. Or you can do something a bit different. You can have a right to left processing unit. So if you look at the second, the topmost orange vectors, you can see that those hidden state receive the sequence in the reverse order. And then you can have them both, and then you can concatenate them, so that when you produce your output, you are kind of factoring the past, the context at your left, and the future, the context at your right. There are applications where you can do it, of course. If you train, I don't know, I've been working on stock prediction, quantitative trading, so enabled with machine learning. If you train a quantitative trading system with a recurrent neural network like this, probably you're going to have some, I don't know, good performance, but you shouldn't allow your network to receive, the future, because the idea is that you can only access to the past. Whereas if you are, I don't know, if you are using recurrent neural networks in language, it might be nice to have a hidden state that represents both, that contains the representation of both the left context and the right context. So this is not rocket science at all. It might seem so, but it's not. So I don't know if you ever use PyTorch. If you use PyTorch, it just, I don't know, 8 lines of code, because there is the RNN implementation already in PyTorch. But if you have a input, generic input, you can just use PyTorch to implement the RNN with 16-dimensional hidden state and 2 layers, one on top of another. Of course, then you need to train it. You need to set up your training data set and all those things that machine learning engineer does. So very, again, high level perspective of it. Okay, questions so far? Okay, cool. Just thumbs up. Pros and cons. Why people were using recurrent neural networks? Because it's nice to have a shared hidden state and a shared matrices for every time step, because you don't have the network to treat different time steps differently, and so you are hoping that your neural network will encode many different scenarios, because you are using just a single shared set of weights, and of course all inputs get treated equally. And then also that in principle you can have sequences of arbitrary length, because you might be encoding I don't know, a tweet or the entire Shakespeare bibliography, but it will be the same for the neural network because you just need to process them one at a time. And the architecture is pretty much flexible because you can stack layers. You just, compared to modern neural networks, RNN neural networks were like super small in terms of number of trainable parameters. And it's nice to have, you know, the addition of the right to left flow of information, because there might be application where you'll need it. But of course, since you need the output of the previous step, you cannot parallelize the execution, because at every time step you need to know what happened in the past. So recurrence doesn't allow you to make, you know, parallelization through time. And also this is a technicality, but when you compute the gradients from a certain time step, what we say is that those gradients are vanishing the farther you go in the past, because again, this is a technicality, but since you are multiplying numbers that are, you know, smaller than 1, the gradients that you are computing, the far you go in the past, the smaller the gradient will be. And if the smaller is the if the gradient is small, you are in a way saying that step in the past is not influencing your updates, your weight updates anymore. So if it's almost 0, that time step is not influencing your weights update. And there might be cases where you need it. There are examples in the slides. So since I do NLP, you'll be seeing examples on NLP, but there are many other applications, of course. So language modeling. When we say that we are modeling language, we are learning a probability function, and we can look at it, at this learning a probability, as we want to learn how to predict the next token given a context. So for example, I have back at the grocery store, Clara bought a something blank, and we as humans know that grocery related stuff is more likely to be there in the completion of the sentence. And that's what we are learning, what we are forcing the network to learn. So we are modeling a probability. Let's say we have a vocabulary. In this case, I'm using words. Our tokens are words, but you can also do it with characters. You just predict one chart at a time. So let's say we have vocabulary. We just need to learn a probability distribution over the words in our vocabulary. So how do we actually do it? With RNNs. Okay, I now realize the text is too small for the slide, but on the bottommost part of the slide, there is our input. So the final part of our input, the grocery store, Clara bought A. And what we want the network to learn is to predict the next word. So for every time step, our target objective, the things that we will use to compute the loss, it's just the next word. So if I'm giving the network the prediction should be our target, our objective should be grocery. If we are giving grocery, we should predict store and so on. So this is something that happens at training time. At inference time, when we want to generate text, and this is something that this is a very one-to-one parallelism ChatGPT is doing when you do your you insert your prompt. Giving ChatGPT a context, ChatGPT has been trained, so the thing that ChatGPT is doing is predicting one token at a time. So in this case, how do we predict the token, the next word? The network express a probability distribution. So what we call logits. You have the logits for the entire, vocabulary, and there are many decoding. We call it decoding algorithms. But the simplest one, the greedy one, is just to take the most likely word, next word, which we expected it to be, if we trained the model in a proper way, we expected it to be something that it's related to grocery store, right? And this is a one-to-one parallelism with what ChatGPT-like models are doing today. Other things we can do with RNNs, we can use RNNs as an encoder. As I was saying at the beginning of the talk, we have been doing some hate speech detection. So since the hidden state is just a vector representation, it's a typically 768 dimensional vector, you can give the network the entire sequence of tokens, and you know that the final state will be the representation of your text, the entire text, since, as we said, it encodes all the previous word in a way. It has been constructed by encoding the past. So since we have a dense representation from a text, we can use it to train a supervised classifier. Again, I don't know about your background, but a supervised classifier is something that tells me if something, for example, a binary classifier is something that tells me if the tweet is toxic or not. I can train it for classical spam ham detection system. It's machine learning model that has been trained to produce a 0 or a 1 if we're talking about binary prediction. Other fun things you can do with RNNs is machine translation. So you have the sentence, "the cat is on the table," very typical sentence from English to Italian translation. And you can use the final hidden state again as the representation of your network, the representation of your source sentence, and then use it as the initial hidden state of a second RNN, which is trained to predict again the next token. But when you train it, you are not giving the network, you are conditioning the generation with the the representation of the English text. But because you are saying the decoder you are giving the decoder network the representation of the English sentence as the initial state. But when you train it, you are again forcing the network to learn the next token, but your tokens will be in Italian. So the network learns tokens, the decoder network learns to predict tokens in Italian, conditioned on the English sentence. So this is a way of conditioning language models. In this case, you can condition on a sentence from another language. There are other ways to condition the recurrent neural network. For example, you can give the network an image as the input. Of course, you need some encoding mechanism of the image. I don't know, there are many, but the point is that you can transform the image into a vector and use it as an input for every time step, and your predicted output will be the description of the image, the caption that you want the network to produce when the network sees another image. And in this case, it's a human hand holding a hedgehog. And I found a very interesting example of image captioning, because you can produce a longer text and you can effectively produce a story. So let me read it out loud. "He was a shirtless man in the back of his mind, and I let out a curse as he leaned over to kiss me on the shoulder. He wanted to strangle me, considering that the beautiful boy had become wearing his boxers." So this is a real example. You can go online and look at how they train the network. But in principle, that's what I showed you here. So you are conditioning the network with an image, and you are letting the network to produce one token after another. So 2 final things, and then we move to attention. How am I with time? Very good. Okay. We were discussing about long-range dependencies. So the fact that the gradients get smaller and smaller and smaller going back in time. And there might be applications or use cases where you need to encode those long-range dependencies. And we have people, we again, inclusive we, people from the community came up with different strategies, different solutions. In these slides, I mainly categorize them in two families: the gated recurrent neural networks and the attention mechanism. So those solutions are a way to get around the problem of vanishing gradient, and also to get around the issue that you have with computation, because you want to parallelize a parallelization through time, whereas with recurrent neural networks you cannot do it. So let's see the two solutions. Gated recurrent neural networks. Okay, I have an example of long-term dependencies, long-range dependencies. Sorry. Yesterday I visited my grandma, and I brought there a bunch of stuff. Also, I installed that Alexa device as you asked. I have strong doubts that it will work, but when you are ready, we can try to video call blank. So if we want to predict the next token, we want the network to encode the past and know that we are trying to call the grandma. So the actor that we are referring the pronoun to is the grandma. So here we need her, because we can try to video call her. And this is a very, we can argue if it's with modern models it might not be that long, but this is a long range dependency, because you need to keep track of the context. And what we in the field suspect that ChatGPT is doing, it's exactly that. It's keeping, when you continue chatting with ChatGPT is keeping track of the context of, let's say, the most recent context of your conversation, just as tokens that have been produced by the model that you entered as prompt. Just the concatenation of the text. So, as we said, the information flow gets cut by vanishing gradients because we are losing the notion of grandma if we are optimizing the network that far away in the past. So, gated recurrent neural networks had in a very clever way, an explicit memory. So explicit memory is something that the network can learn to use, erase, modify, or get rid of it. So, and this is a very old idea, 1997. And an example of gated recurrent neural networks are LSTMs, so long short-term memories. And it's quite complicated for this hour of the day, but what you can see is that you still have the input and the hidden state, but then the authors added what they called explicit memory, this C of T, and then you can change this memory. You can force the network to learn how to use this memory. So there is a gate mechanism that is what we call forget gate, and it's basically how much memory you forget at every time step, and you let the network learn this thing. And so there is a input gate. So you let the network learn by itself how much of the input the network should use. And there is a third gate, which is the output gate, which is, forces the network to learn how to discard from the output. I'm not gonna go super detailed here, but that's the main idea behind gated recurrent neural networks.
I have a question.
Yeah, question.
So, what is exactly the problem that we're trying to solve here? That if I understand correctly, that we are carrying over too much context, or is that
exactly? So, we need to keep track of the context. So we might hope, in a way, that the context is still encoded in the hidden state, because we just have one single hidden state in the neural network. So initial recurrent neural networks were just like that, and people, at a certain point, they realized that you cannot squeeze that much context into a single hidden state, So you just need another explicit memory that you can. The idea of having learnable gates, it's something that lets the network understand what kind of information it should use, what kind of information it should discard. So you still have you have the hidden state, but you also have an explicit memory, which is another dense representation. So it's another vector, 768 dimensional vector. But yeah, the two novelties are the new memory cell, which is the explicit memory cell, and those learnable gates. So you force the network to learn how to use that information.
And are those simply weights?
Yeah, basically it's again a projection of the input, and then there is a sigmoid function that produces an output, and then you multiply the output by the x, and so in a way you are weighting the x with a number, a scalar number between 0 and 1. Welcome.
Any other questions?
Okay, we can move on. So this is not parallelizable again, because it's something that goes from, you need the output of the previous steps to compute, C of t, because you need C of t minus 1, H of t minus 1. So you still have that dependency. And in a way, if the sequence is very long, and when we deal with very long sequences, we're dealing, for example, with books. Let's say we are encoding a book, and we need a representation of a book. The explicit memory might not be enough. So what people came up with in 2016, late 2015. Yeah, it's 2015, I would say. It's the attention mechanism, which is, again, it's safe to assume that this is the one of the most breaking through innovation technology advantages. It's late. It's quite late. For AI, like in terms of discoveries in the AI community, because there are many neural networks today, and I would say 99% of them are based on some sort of attention mechanism. So, and this is a very clever idea. We don't know what motivated the attention mechanism, but basically we are mimicking what humans are doing during a cocktail party. So when there is a lot of background noise, and we learn, in a way, it's our innate ability to learn how to filter. You have a low pass filter, and you just discard the background noises, and then you just keep chatting with the people that are in front of you. And so you learn how to. We have this ability. We learn how to discard all the non-relevant information, and we just use the information that is relevant for the very moment. So that's something that completely changed the field, and it didn't change only the NLP field. It changed the field of physics. It changed the field of vision applications. It changed reinforcement learning, like what you have seen, AlphaGo, AlphaZero, everything. Every neural network in those models is based on some sort of transformer, which in turn is based on attention mechanism. So I'm gonna show you some example. The initial setup the attention was designed for. Our beautiful English sentence, cat is on the table. We are translating it. So we have already seen that you have two recurrent neural networks. You have an encoder neural networks which gives the initial state to the decoder neural networks. And then we have the problem of vanishing gradients, because when we are predicting this token, the very final token in the translation, we are saying that the previous hidden state is encoding all the past, so it is encoding the previous generated tokens in Italian, but it's also encoding in a way everything that came from the English sentence. So this is a very in a way it's a bottleneck for the information, because again it's something that it's difficult to keep the information or retain the information. It's also difficult to train the network because you have many steps and your gradient is squeezing. So this is the bottleneck. What people came up with, it's a direct connection. So this is a very simple and clever idea, but what people were doing, for example, in this case, we are predicting the first. We are predicting the first token in the sentence. So instead of just using the final hidden state in the source neural network, we are learning another set of weights that are just dot products between the current hidden state in the decoder and every other hidden state in the source send in the encoder network. So you compute this dot product, and this is a way that you can learn, and that's what we call attention weights. So the network is learning how to pay attention. It's anthropomorphizing everything, but it's in a way it's learning how to weight every step in the past. So and this is something that the networks learn through training, but the crucial point here is that the network, okay, the graph is somewhat, because it's completely wrong, because every dot and every dashed line should, there is okay, it's very misleading. I realize that it's very misleading, but yeah, it's very misleading. Every dashed line is the product between an hidden state, a time step in the source encoder, and the step we are producing, we are building now in the decoder. So the network is learning. So imagine that those dashed lines are like connecting every step of the encoder with in this case the first step of the decoder.
I have a question.
Yeah, of course. We have.
So my question is that now, should you keep storing the hidden states from the past?
Exactly.
Okay.
That's
so that
that's a
explodes in memory.
requirement. Yeah.
Okay.
That's a requirement. That's why, and this is, something, you have to trade off something when you're doing this stuff. You cannot encode any arbitrary length sequence, because you need to keep those weights, especially if you have multiple layers. You need to keep those embeddings, those hidden states, because you need to compute, it's what we call, it's a O2 in terms of memory, because memory footprint, because you keep the attention. The biggest limitation of attention is that it's O2 in terms of memory footprint, because it's every token with every other token. That's why people are doing many crazy stuff to, learn sparse attention and do something else. There is a question.
So, of course, you have to keep in memory everything in the past, because otherwise you cannot multiply. But what once before was degrading, like a gradient of forgetting, wouldn't in this case just uniformly get forgotten over time? Because if you're building up a very big database of information, everything has a very tiny weight, even the most important words. So is there any way to have a hierarchy of information and how it is contained within other information? I'm sorry, I'm coughing.
Yeah, no worries.
I'm done. Sorry.
No worries. So, okay, about the amount of information that you need, you typically, when we moved from typical recurrent neural networks to large-scale language models, something that is built now today is built on top of a transformer, which is an abstraction of the attention mechanism. You typically need much more data to keep it like in a way that produces meaningful stuff. This is something. But then it's a completely data-driven process. So you don't have, if that was your question, you don't have a preference over the layers. You don't have, you have the layers communicate. So you still provide the next layer, the previous layer hidden state, but there are no way you are not treating layers differently. You compute a set of attention weights for every layer in the network. And the thing about the gradient, the vanishing gradient, gets in a way fixed because you now have a direct connection between the tokens. So your gradient update will just need a single, you know, the chain rule of when you decompose the gradients, when you are computing the gradient of the loss with respect to the inputs, this chain of multiplication will be shorter. It's just a matter of one or the number of layers that you have in the network. Like, again, not super technical here, but the point is that you can have the phenomena where the network is not learning everything, but typically it's a completely data-driven process. You know, BERT, for example, which is a transformer-based neural network, was trained on everything that was available online in terms of English text. So books, Wikipedia's pages, everything that was on the internet. And then we are keeping doing this for larger and larger models. Then, of course, you need to curate your collection, but it's a matter of scale in terms of data side. Does the answer your question?
So all of this is entirely on training.
Exactly.
So when I'm just talking with ChatGPT, I'm talking about two different topics within the same chat because I forgot to change chat.
Yeah.
And like I talk for a long time about the topic A and then shortly about topic B. Then there are two sets of information that are mixed together. So all this thing does not apply there, or does it use the weights that learned before?
Exactly.
So how does it keep the two topics separate without mixing them together?
Because, okay, and now I'm speculating, because behind ChatGPT there's no paper, non-official paper. So we
Okay.
don't know what the training data is for ChatGPT. There are a bunch of papers before ChatGPT which illustrate how those models were trained, because there are some tricks. And I can point you later to those papers. But in principle, you have everything. All of that is happening at training time. And once you have trained the model, you are not gonna change it. So I believe I'm not in contact with OpenAI, but I believe that they train it once and they deploy it, and they just keep tracking of what the user are using as input. They are providing the model as prompts. And this is an interesting stuff because, you know, behind ChatGPT there is OpenAI, the company, the San Francisco company. They released GPT-3, and you could use GPT-3 through the APIs online. There was the Playground API before ChatGPT. Now, a very big component of training ChatGPT, we know that for sure, is the prompts that people have given to GPT-3. So they are using prompts that people have used on their platform to train the next generation language model. But all of that, once you train the model, you just fix it, like freeze it actually, and you deploy it. And when you change topic in the conversation, and the model is able to answer your question, even if you are changing topic and you are referring to a topic very far away in the past, it's because they have trained the model properly. Just that I don't think there's like a very specific mechanism there that it's working to keep track of the past. It's just they had high quality data, and they can handle very long sequences. And you can since it's O2 in memory requirements, you just need many GPUs or many TPUs, whatever, to process your input. But we don't know that for sure. I mean, there's no scientific paper yet for ChatGPT.
So, can you hear me? Yeah. So, what is the dimension, let's say, of the attention vectors? Because you say you are O2
Okay.
n square, let's say, but with respect to what?
Okay. O2 in the length of the sequence. The maximum length. You typically have on those models a maximum length that you can handle, which is a number between. Typical models that we use for research stuff are 512 or 1024. You get with the powers of 2, typically. And that's why you need the moment that you increase your sequence from maximum sequence length, you get the O2 burden. That's what the O2 stands for in terms of memory footprint. And the hidden state in typical language models today are just 2048 dimensional floating point vectors. That's the typical averages. And so the attention weight itself is a number. It's a number between 0 and 1, and they act as a distribution, discrete distribution, probability distribution, because they sum to 1. So what we are learning with attention weights is how much of the context, how much of each time step we need to carry with us when we are generating the next hidden state representation. Now it's more convoluted than that, but the attention weight is a number, and it is used to weight how much of, in this case at least, how much of the previous time steps you want to consider. So what you are actually training is not the attention weight, because the attention weight is a floating point number. It's the representations themselves. It's more convoluted than that. We can discuss about it later.
One last question that probably you may want to take it to the end, because I think
we are very close to the end.
I'll be quick, but we can talk about it later. So basically, the attention mechanism, as you said, is a mechanism that describes with the numbers that we obtain through this learning process. We are basically saying how much of the how much context we are carrying over.
Yeah.
Regardless time constraints.
Exactly.
Right. So the follow-up question would be, and we can answer that later. One very introductive talk that I've attended was about how some of these models, when trained, do not really account for the time where the data came from. Some of these models were trained over I think it was discussions in the Congress, American Congress, that date back to 200 years and stuff like that. So when you use those kind of models, they are biased in a very weird way that does not account for the way times have changed. So the question would have been whether this mechanism or other mechanism are trying to impose an idea of time, as in age over the training set.
Okay, it's a very there is an area. Actually, there is an area of research on adapting through time language models, because people went crazy when BERT went out, when BERT was released, which is the very first large scale language model. But BERT was trained with data from the internet up to the 2019, I think. And people were keep using BERT. Actually, I think BERT is still used today. There are $7 million per month of BERT. But BERT is trained with data on up to the 2019. But doesn't know anything about the COVID or anything else that happened from the 2019. So it's a very active area of research. We can discuss about it later, but there are some works on that. So I'm about to conclude. There are 2 slides left. I just give you some examples of what people were doing with. Now everybody's talking about ChatGPT, but there were DeepMind researchers back in 2013 that were using the architecture I showed you here, which is again misleading because the dashed lines should not be there, to, for example, generate handwritten text. So the first line is written by a human. All the other lines are not written by humans but are written by a AI, where the task was to predict the x and y coordinates of giving. So you can unroll the pixels and the x and y coordinates, and that becomes a sequence. And then you can let the network learn what's the next x and y coordinate pair of coordinates. And so you can so they were using classical encoder-decoder neural networks, and they weren't working until they realized this is one of the first example of attention mechanism, and these are the attention weights. So basically, when you are generating the letter, you can see that the attention weight is mostly focused on the letter itself in the text, but it's a technicality. But again, this is a number. The attention weight is a number, which is weighting how much context we are retrieving. So that's basically the last slide. There's a last slide. We've been talking of technologies that went from 2010 to 2016. So of course there's a lot more on there. But I kind of liked to, starting from the basics, starting from the foundational technologies and why we needed that. And the idea is that if you use RNN with attention, you still cannot parallelize it because you need, the processing through time, even if you store the hidden states. What people developed in 2016, which is, I think, the most I don't know how many citations this paper has. You can look it up online. They invented the transformer, which is now the core technology behind everything we are doing in NLP, vision, reinforcement learning, whatever you can think of. And I used to have the last sentence in this slide, like the transformer is the building block of modern language models, but in reality, it really took over every field that AI is dealing with today. So you have BERT and GPT for language, but you have VIT, vision transformer for vision, WOV2VEC for audio signals, and so on. So with that, I'm basically done. Thank you for your attention.
Are there any other questions? There's a few.
Couple of questions.
Yeah, this is probably more philosophical than technical, but I see probably in some cases some analogies that are a little too much stretched, in my opinion, with how our brain works. I mean, even in terms like attention and stuff like this, it's something, I don't know, that is wanting, is misleading. Are we really learning to build this kind of neural network looking at how our brain works, or is just something randomly similar? I don't know.
Okay. I know some neuroscientists are like not super happy that there are those parallelism between at least the neurocortex and our neurocortex and transformer models. I don't think they are learning the way we do, like learning the way we refer, like we solve problems as intelligent beings, because they are statistical models. In the end, what we are encoding in the weights is again a probability model. Just once you look at it from the right perspective, it's just a probability model.
Our brain works, I think.
I mean, I'm not an expert on in the field,
okay.
but I don't think we reason for following probabilities. So there are works that today, since we have those capabilities with language model, you can express, since the language is the thing that lets you express many, you know, you can ask ChatGPT to ask to explain to you a joke, for example, but that's a probabilistic view of, you know, solving the joke, because it has been embedded, you know, in the training data. It has been embedded. It was in the training data. There were examples that were showing how to solve a joke, how to explain to someone a joke, and then in a way the model is learning to generalize. So because we can express through language some, you know, generalization capabilities, because once I learn out what are the words that I need to explain a joke, if the joke changes, I can, for example, you know, find a way to explain the new joke. But I think we're still trying to figuring out what in the statistical sense. So very far from, I think that's my opinion, I believe it's very far from human intelligence. We are still trying to understand what are the processes what are the neurons that get triggered when you ask ChatGPT something. There is a very interesting field on mechanistic interpretability. It's a very niche field as of today. Like there are, I don't know, less than a dozen papers on that. People try to understand what's going on in the weights of those models. And while there is a very large body of research on emergent capabilities, emergent properties. So I think it's still, since we are saying, I think we're still saying that we are far from human intelligence, but I think as a curious species, I think we should be looking into those models as tools. So the tool that is explaining a joke, it's still a very meaningful result to me, because, you know, we don't need to associate them to intelligence, but we can associate them with very powerful tools. Because, for example, I never remember the API, matplotlib APIs, and I'm Stack Overflow every time. I just need something that provides me the answer as fast as it can, and it solves a really practical question, like a hammer. You need a hammer for doing something. You can use ChatGPT or ChatGPT-like models to solve a related process without the need of associating it to intelligence. But I'm not super expert on the neuro-computational part, I have to say.
There was another question.
Yeah.
Thank you. So, were transformers used also on like time series data, and
Yeah.
how those architecture are different from this?
Okay, we didn't talk about transformers. So first thing, they get rid of the sequentiality, the need of processing time steps one of after another. So that's one thing. And second, there is I can give you some examples. For example, again on the quantitative training aspect, when you need to model a stock prices or a set of stock prices, and yeah, there are works. You just the title of the paper is "Attention is all you need," because to process every time step, you just learn attention weights and transformation based on attention weights. And I think one of the reasons behind the success of the transformer is that the transformer doesn't care about the nature of the input. So if your input is a I don't know, it's a one token given a vocabulary, it will work. If it's a representation of your stock price in the last 15 days or 15 minutes, it's gonna work anyway. But yeah, to really answer the question, we would have we would need to go through the architectural bits of the transformer. But it's basically something that doesn't require the sequentiality, of, like processing the input in one time step after another.
Any other questions?
So before feeding the embedding in the transformer,
Yeah.
why do you need to encode the position? I mean, if you switch the token in the yes, if you switch the position of the tokens, at inference the output will be different.
Yeah.
So why do you need to encode the position in the embeddings?
Okay, that's something that they tried in the paper, and then it was replicated on the first language models that are based on the transformer. But already in the initial paper, they had this notion of positional embedding, and because the community back in 2016 was using word embeddings, WOV to VEX. You know, I don't know if you know about word embeddings. Those word embeddings are in a way static, and you are once you learn your word embeddings, you will have a single word embedding for the word. So if the word is cat, you're gonna have a single representation of cat. That's your representation of cat, and it's you are not gonna change it depending on where is it in the sentence. What they did in the transformer paper is explicitly encoding the position such that the representation there will be a static representation of cat, but I want it to change not based on the position of the where cat is in the sentence, because there are for example, since basically attention is all you need paper was a machine translation paper. That's why I brought today many examples on machine translations. You need to know where the word you are attending to is attending to is not English probably, but the word you are computing your attention weight against should be different if it's at the beginning or if it's at the end, because the meaning might be different in the sentence that you are using to the code. And that's, you know, again, a very important technological breakthrough, because people were just using a single representation for a word. Once you have it, you're not gonna change it, and you're not gonna, you know, use it differently. That's it. Instead, the positional embeddings lets you have different representations of the same word, and you can still disentangle them, because you have the the static embedding, and then the position, and before summing them, you can just keep one of the two. For example, if you need the static representation. Transformer have static representations of word too before the sum.
Let's take the last question that we had, and then
Pizza.
we can continue over some food.
Yes. So first of all, thank you for the nice overview, because not being at all technical in these things, I think that you gave a sort of like a great leaflet of a map that I can dig into more. One thing that is, I think, very relevant to nowadays is that, in my just lame understanding, is that, for instance, things like ChatGPT, right? So they've been trained on this big corpus of text and so on. And so that's why they called about these billion parameters. And as you said, is like ON2, because, okay, you solve the problem of sequentiality for computation, but still you have so much great parameter. So let's say, is there any hope for somebody that wants to play on his own PC on something similar? Could you say there are some sort of like field of application or field of like tutorials, things that can give you great result and satisfaction that you cannot speak like in a ChatGPT in your PC? You cannot train it with your PC. But maybe there is something that you can get the same satisfaction in doing so. Thank you.
Okay, that's a wonderful question. I think a very original and wonderful question. I would say fortunately the answer is yes, because where I work, we are like a small academic group, and we don't have we don't have the computational power to, even doing just inference, because when you are training those models, you need to keep track of the gradients, again, memory footprint. But for inference, at inference time, you don't need the gradients. But still, if you have a 1.5 billion model, you cannot, if you have a single GPU, which is a customer, the classical NVIDIA A5000 or 6000 something, you cannot even, put the model into the VRAM. But the answer is yes, because there are mainly two options, and also something that it's like hardware is keeping up with in the game. So you can have, okay, let's talk about the hardware. You can train a GPT-2, which is a smaller version of GPT-3 in a way, with a smaller set of parameters on this laptop today, because of hardware optimization, because Apple Silicon and whatever. But I've been doing some training on this very laptop, and you can have a pretty decent generation. So if you have a very specific task, you don't want a ChatGPT like chatbot. You have a very specific task. I want to, reply to my customer service for my customer questions. I can train that on a smaller laptop, and of course many versions of them on a bigger GPU, single GPU. And the other option would be efficient training. There are some works that are training only part of the network, not every parameter of the network. If you have 6 billion language model, and it's no later than yesterday, Hugging Face, I don't know if you know the company, Hugging Face released a new library that collects several ways to train a 6 billion parameter model that are based on some efficient tricks. So you are just tuning a very small set of parameters. You don't need to have access to the entire set of parameters, and you don't need to change them. You just need to change a very smaller set. And if you change the smaller set, you still have a very good language model. And if you keep everything else frozen. That's it.
Okay, one last couple of words. First of all, another round of applause for Giuseppe. Thank you for being here. It was great. One last few words. Thank you to Daniele and to help with who helped with the organization. Thanks to Luca, who's helped as well. Thanks to Matteo, who's been our DJ and director for the night. And thanks again to eDreams, because tonight they're offering us food and drinks. So if you want to give a talk, on any topics, Giuseppe, if Giuseppe will want, will be back with us and explain another part of the topic, that maybe do some demos or even, since he mentioned a few things that we could try. But of course, this is open to anyone. So if your company wants to host or offer, sponsor the meetup, want to sponsor food and drinks, wants to bring us here some speaker, please let us know. Hope you enjoyed the night. Let's do it again soon. We are planning to do another one probably April or so. But if you want to propose something, please do. Thank you.